Hello and welcome back to this NPTEL course on advanced plasticity of solid continuum. So, if you recall, we have just started embarked on the journey of our visco-plasticity with thermal effects, that is including heat transfer. And I was telling you about in the last lecture, I was telling you about how to derive the generalized heat equation, and we almost were there when I stopped it and giving you time to assimilate things. So, I hope that you have done that so that we can come back to our pursuit of the generalized heat equation and its interpretations. Okay. So, here we go. Now, when we ended the last lecture, we had two different representations of theta eta dot, right. This was one expression for theta eta dot, right, you remember, and the other expression for theta eta dot is here. Okay. So, just equate the two, that is all we can do now. If you do that, equating these two expressions will lead you to this. Okay. Now, all that is left is to exploit the Fourier's law of heat conduction, which says that if K denotes the linear conductivity, the coefficient of heat conduction, right, then Q, that the heat flux will be minus this conductivity times gradient of theta, right. So, put that here, okay, so that this term becomes with a plus sign K. If K is constant, the conductivity is constant, K Laplacian of theta. You remember that Laplacian is nothing but the divergence of the gradient of theta, okay. That is how the Laplacian is defined. All right. So, that you can do, that is the Laplacian of theta. If K is of course a function of theta itself, which is possible, in that case this term becomes, this is not correct. In that case, this minus divergence of Q becomes equal to minus divergence of K, which is possibly a function of theta, right, grad theta. Okay. Then you cannot really write it like a Laplacian. All right. That is what I have actually done here, but this minus and minus will cancel. So, this becomes plus, because Q is again minus K times grad theta, right. So, basically this is the one term, which is basically the diffusion term, irrespective of this form or this form. This is a diffusion term, right, with a variable. So, K is also called the diffusion coefficient. In this particular case it is called conductivity, but it is also called in the more general physics and maths literature, it is called the diffusion coefficient, right. So, so this is that standard heat equation has this term, the diffusion term, right. And then there is this R. So, on the left hand side we have CV theta dot, okay. Then the third term is X alpha dot, inner product, appropriate inner product. The fourth term is theta del sigma by del theta, inner product with epsilon dot. The fifth term with a minus sign theta del x by del theta alpha dot. Each one of these terms, especially this and this, have profound physical meaning. In fact, this term has also got a profound physical meaning, right, but we have discussed that some time back, what this term does. It actually tries to flatten the undulations in an initial initial profile of theta, okay. Whatever initial profile of theta you give, temperature, initial temperature profile, it will try to flatten it over time and make it the same as the ambient temperature in infinite time, right. So, that is the effect of the diffusion term, that we know already, but the other three terms are the most interesting, right. So, let us talk of the third term on the right hand side. Which term is it? X alpha dot, okay. This term is basically a representation of the mechanical dissipation, because alpha contains all the internal variables. X is the corresponding force due to the flux alpha dot, that is this mechanical dissipation, if you give sufficient time for it to dissipate, then heat will be generated based on this, right. So, basically this mechanical dissipation is in long term is a sort of representation of the heat generated, but not all of that can be traced to temperature rise, right. The full of this dissipation need not go to temperature rise, because the heat, some of this heat that will be generated will be used to fire the microscopic changes in the microstructure. That will not come, because the energy, heat energy, part of that is going into changing the microstructure, right. So, that cannot come as temperature, right, because that is already spent in changing the microstructure. So, this is a very important thing. X alpha dot is your mechanical dissipation, right, the total plastic work, let us say. In the Perzina model, in fact in all models, most models, it is always non-negative. It is plastic work must be non-negative. It can be 0 if there is no plasticity. Let us talk about the fourth term, right. The fourth term is this. This is what, this term is basically called the Piezo-Caloric effect. You see that what is actually happening through this term is that sigma is changing, or I would say sigma, as sigma is changing, temperature is getting affected, right. So, this is the Piezo-Caloric effect, which essentially tells you that if there is a change in shape or size of the body due to mechanical deformation, that may lead to heating or temperature change. Like for a gas, if you compress the gas, that actually can give you a temperature rise. Okay, so basically this is a similar situation for solids. Most people typically ignore this effect. It is seen typically not to be very significant. There could be exceptions, right. Let us talk about the fifth term, this. Now, this term is essentially the forcing, the thermodynamic force X changing alpha, microstructural rearrangement, which basically, so this term essentially it is the thermoplastic coupling. So, the plastic microstructural rearrangement affected by the thermal effects, right. So, it accounts for how the internal state changes, like dislocation density, this varies with temperature, right. So, you see these are the three effects that we have seen, right. So, now let us understand. So, basically in a grocer's shop language, it is something like this, that is, I have this much of energy, plastic work done, right. That is all that I can spend to generate heat, right, in whatever form, to make things happen in the microstructure. Part of that probably will go into here, part of that will probably go into here, okay, and part of that will go into the dissipation, pure dissipation, so dissipation of the heat, okay. So, how much, that is the question, how much will go where, that is a detail that we need to work out. So, it is here that the Taylor-Quinney coefficient comes in very handy, okay. So, as I told you some time back, the Piezo-Caloric effect is something that most people think is not very important. Experiments have not shown us that they are very important, I mean in most cases. So, let us ignore that. Also ignore the external radiation, that means the heat source R. Let us say there is no heat source, right. In this entire the equation for the generalized heat equation, these terms with arrows, not this is the diffusion term, this this double line, arrow with double lines, these terms essentially are the source terms. These are the source terms that are generating the heat, right, and this is the term with a single arrow that is dissipating that heat, trying to dissipate the heat, may not be able to do it fully, right. So, these so basically if you ignore the piezo-caloric effect, there are only two source terms, which is basically one is the total plastic work and the other is the thermoplastic effect, right. These are the two source terms in the heat equation. So, therefore, this must be equal to Q dot, right. Q is the heat. Remember that this dot has to be represented properly, because as I told you in the last class that this dot is not a proper dot because heat is not a proper state. Okay. So, the total plastic work Wp dot, which is which is obviously x alpha dot, right. This is what is written here. Okay. That is all that we have actually worked. Because of plasticity, this is the total work done. The Taylor-Quinney coefficient now tells you how much of this work goes into temperature change, that is through heat dissipation, strict dissipation, and how much of it gets stored to change the microstructure and never goes into temperature change, right. So, clearly this is the thermoplastic effect is this stuff, is the energy rate which goes into the creation of a new microstructure, changing alpha. This is the total, divided by the total must be the rate at which, divided by this total must be this beta, right. So, this is Q dot divided by Wp dot. Okay. So, this is the Taylor-Quinney coefficient. The question now is, what is its value? It cannot be more than 1, obviously. How much is it? So, that is a question that we need to answer. If you try to simplify this expression for this Taylor-Quinney coefficient, you get something like this: beta equals 1 minus theta x inverse del x by del theta alpha dot. Okay. This is a simplification of the same expression that we had earlier. The question is now, what should be the value of beta? Is it a constant, right? Many people think, I mean, as an approximation you can treat it as a constant, which is probably not right. Okay. So, the energy which is not converted into heat and hence into the dissipated dissipation in the form of temperature, varying from point to point and finally reaching a constant level, that is called, the part which is not part of this is called the stored energy of the stored energy of cold work. Okay. So, this is given by the thermoplastic effect. This energy is trapped within the material's microstructure, right. So, you can think of this also as a heat, but this is not the standard heat what is written here, not that. It is a generalized form of heat called the configurational heat. I need not get into the details of that, because that will further confuse you, because it is already a pretty the course is slightly advanced. So, I do not want to further get into difficulties, but you see the energy that is trapped in the material's microstructure must remain there for the microstructure to hold, right. Otherwise, it will go back to its original structure, right. So, this microstructural change may be in the form of dislocations. There could be other forms also of microstructural change due to plasticity. One of them is the phase change, Martensitic transformations, which means that there could be a kind of a very brittle formation of semi-stable kind of states, right, which happens typically. Martensite means if you actually during steel making, for example, if you quickly quench, that is reduce the temperature of the steel specimen, then it actually sometimes undergoes, depending on the quenching rate, undergoes a very brittle transformation. It becomes very brittle and very hard, right. That is called a martensite. In this case, there is no quenching needed. It is the internal heat configurations which are changing, adjusting itself because of this plasticity. Because of that, you can actually get martensitic transformations, phase changes and residual stresses. These are stored because there could be these grains or the plastic crystals which are there, they may actually undergo elastic deformation, right, at the grain level. And so because of that the residual stresses may be actually there. Okay. So all these effects are there in the form of this trapped energy, all right. Now let us talk of how we can actually determine beta. Okay. One way of determining beta is very simple, that is do a model. Based on our model we are finding all the quantities of interest, right, all the quantities. We will find theta, we will find x, we will find alpha, everything. So we can actually calculate beta based on that, but that is purely model driven. People may tell us that okay, this model is not to my satisfaction, it may not be very accurate, so I need an experimental determination of beta. That also can be done, but you need to have basically have a simultaneous measurement of the mechanical work and the resulting thermal energy for that, right. So for the mechanical part of the measurement, that is x alpha dot, a specimen must be loaded very fast. Why? Why can't you load it slow? Because if you load it slow, you are calling for trouble by allowing the dissipation to take place. If heat is dissipated, then part of it is gone. So therefore the accounting is not proper. Accounting of the energy, which part has gone into what, is not proper, right. So you must load the specimen fast enough so that no time for conduction of heat is allowed. Okay. So this loading therefore is of a high strain rate. One of these ways is to use a split Hopkinson pressure bar, right, in which you can actually generate an input loading rate of about in terms of 100 meter per second or something like that, even more, right. So the plastic work therefore can be calculated based on the area under the stress strain curve, right. This area is given by integral of sigma inner product with d epsilon p. If you can calculate it by measuring it fast enough, then it is not a very simple experiment, but in principle yes, it can be done. Okay. Then comes the thermal measurement, because we must also understand what is the temperature change, but over a very small time and locally, right. So for that we need to use high speed thermography, which is based on infrared, or instead of that we can use fast response thermocouples, right. This will be measuring delta theta, but again this fast response is a very important thing, because you can't allow the time for the heat to conduct away and therefore spoil your calculations. So if you are able to do this experimentally, therefore you are doing it very fast, so therefore you can assume adiabatic conditions, that means no heat transfer, that means very little. Okay. So high enough, the rates are high enough so that no time is given. So therefore the heat generated is nothing but Q is equal to Cp, the specific heat capacity of interest, times delta theta, right. That is the heat generated. So you basically divide this heat generated by the total plastic work which you have calculated experimentally, and that gives you beta, right. So it is true that experimentally beta has been determined for many experiments, but it is not true that across different experiments you get the same beta. It is certainly not true. The practitioners often use beta equal to 0.9 as a convenient rule of thumb, which is far from the reality, right. This is usually not the case, that is beta is not a constant in many problems. For example, I will give you some examples. Okay. So suppose the strain is low. So low strain means that there is a large fraction of energy that goes into the nucleation of dislocations. That means a lot of energy goes into the creation of new microstructure initially, because lots of dislocations are created due to the plastic flow, right. That means less energy from the plastic work, which is x inner product alpha dot, is available to dissipate as heat the way that we understand heat, that increases temperature, right. So that means that beta will be low, right, it will not be 0.9. If you start an experiment of a pristine specimen which has not undergone much of plastic flow earlier, and there is a lot of dislocation generation, nucleation, then beta is pretty low. Okay. Now typically dislocations cannot go on increasing indefinitely, so it saturates, right. So if it nears saturation, then less of this work will be needed from the overall plastic work to be for the conversion of the microstructure, right. So that extra energy that is available, extra power that is available from plastic work must go into the dissipation of heat, so therefore that will increase beta, so higher beta. Okay. So depending on the problem of interest, depending on at what stage the specimen that you are using is there in its plastic deformation, right, beta can vary, and that is a very important thing, right. Now we can return to our variational scheme, right. So all of this has given us some ideas, right, about what basically the generalized heat equation does. It gives some insights into how the physics of plasticity happens. That is why we talked about it. But come to the, essentially this differential equation for this theta is never, we do not have to actually directly integrate it to find theta, because we can do everything based on our variational scheme, right. So for our computational purposes, that heat equation is not very useful. So let us come to our computational thing within a finite element framework. So the dissipation arises from two sources here, then again, if you recall, viscoplastic flow and heat conduction. Now as we have done in the standard Perzina model without heat transfer, here too we start with phi star, okay, that is the dual to the dissipation potential. Think of this phi star now not just a function of sigma, but also a function of x, which are the extra thermodynamic forces that will arise because of the hardening, also a function of g. Theta is basically not, directly not forcing anything. So basically these three are the quantities of interest. G is what? G is basically minus, sorry, this is G. This is the thermodynamic driving force for heat, which is given by minus grad theta by theta. If you do not put a minus here, then it is difficult to be consistent with Fourier's heat conduction law. So as so that is why so G is basically the something related to the gradient of temperature with a minus sign. Now split phi star, okay, into the two parts. One is the mechanical part, call it phi Vp, viscoplastic part. The other is called the thermal part, right. This thermal part is simple. It is a quadratic form for G, right, because G is the driving force now. If you recall, phi star is a function of the forces or the generalized forces. Phi is a function of the rates or the generalized rates, right, okay, to which these forces are conjugate, okay. So now therefore you see, so phi star has to be written in terms of these forces. So G, half of G times k theta times G. So times means with an appropriate inner product, dot product here, okay. This k theta is not the directly the conductivity, okay, heat conduction. It is related to that, because there is a division by theta here and all that. So basically it is a function of this original heat conduction and theta together, okay. So it is related to the heat conduction. This is the thermal part, this is the viscoplastic part. If you see that the viscoplastic part is same as before, we have the Macaulay bracket. This small k theta is possibly is the basic heat conduction coefficient. It can be a function of theta, okay. But this capital K theta is a function of this small k theta. So that is why we need two different k thetas, okay, here. Okay. So this Macaulay bracket and m here is basically the rate sensitivity exponent. Mu here is basically the viscosity, right, in the viscoplastic flow. So, earlier we used eta for viscosity in first introducing the Perzina model, but later on I realized that eta we are using also for entropy. So, I should not mix things like that. So, therefore, I changed it to mu. Okay. Please do not get confused, mu is basically the viscosity coefficient. So, these are the two terms, right. So, we can call this as this term as phi star theta, so not theta, theta means phi star thermal, and this term we can call phi star Vp viscoplastic, alright. So, these are the two terms we have. Now, let us talk about the dissipation potentials. So, the fluxes are obtained by the appropriate subdifferentials, right. So, these are very simple that we have been discussing for a long time, but here there are multiple variables, right, multiple forces. So, epsilon p dot is the subdifferential of phi star with respect to alpha, with respect to sigma, I am sorry. Okay. Alpha dot is the subdifferential of phi with respect to x, right. Q is the subdifferential of phi with respect to g, right, and all this. So, Q here is the heat flux, which is the generalized flux corresponding to the thermal force, which is minus grad theta by theta. Okay. So, this term basically if you do, it is something similar to the Fourier's law, right, but there is a it is not exactly written in the, so basically this is a mistake, this should be G, right, this is a mistake. So, but G is grad theta by theta, right. So, it is not exactly Fourier's law, it is related to that. We can derive Fourier's law from here. Okay. So, now based on this expression for phi star, our objective is to find phi by a Legendre transform, okay, Legendre-Fenchel transform. So, the Legendre-Fenchel transform and its dual structure is such that if the dual has an additive structure, then that will be replicated even in its transform. So, therefore, phi will also have this additive structure, right, and phi Vp will be a function of epsilon p dot and theta, and phi thermal part will be a function of H, which is basically scaled flux, thermal flux. So, heat flux Q by theta, right. So, this is basically the conjugate flux to the thermodynamic force Q, okay, the thermodynamic force G. Right. So, let us obtain theta. This is again a pretty straightforward exercise, right. So, now for the thermal part, it is very clear because the phi star is quadratic in G, phi thermal will be quadratic in H, right, with a k theta inverse, which actually directly follows from the Legendre transform. I have not shown the details here, some details are here, but it is expected that you actually derive it given the simplicity of this expression, right. So, this is the expression for phi theta, because we have been discussing about the Legendre-Fenchel transform in different aspects for a long time. Now, to obtain phi Vp, we have to use the function, the yield function f sigma. Let us consider the simplest yield function, which is of the von Mises type, except that sigma y is now a function of theta, right. So, the viscoplastic strain rate therefore will be given by the flow rule, which is the subdifferential of phi star epsilon p dot equals subdifferential of phi star. You can differentiate this phi star expression, the phi star Vp part, with respect to sigma to get this relationship. Del f by del sigma is the unit normal Np to the yield surface, to the yield so-called yield surface, right. So, basically in terms of this del f by del sigma written as Np, you can write this, okay. So, you can write epsilon p dot's norm as 1 by mu, the viscosity, times f by k to the power m, from which we can actually find f, right, to be equal to this, right. Now, let us take the Legendre-Fenchel transform to get Vp. So, Vp is basically the Legendre-Fenchel transform of phi star Vp, provided this is minimization with respect to sigma, but we have already got that minimum sigma. So, I am putting that sigma inside here. Okay. So, you understand. So, that is why I have not put that supremum outside. Okay. So, sigma epsilon p dot can be written, this part can be written in terms of sigma 0, because you know sigma is now, because of the plastic flow, it is on the boundary of f, right. So, basically sigma 0 is equal to f plus sigma y. So, sigma now will be given by the overstress plus sigma y, f is the overstress, right. So, f plus sigma y norm of epsilon p dot, right. So, substituting this expression for sigma epsilon p dot, the stress power, into the expression for phi Vp, we get this detailed, you know, expression for phi Vp. To this we add an extra term, which is this. This is not, this is the rate independent part of phi Vp. Okay. So, there are two parts of phi Vp, one is the rate independent part. This rate independent part does not affect phi star, because corresponding to this rate independent part, phi star will be 0, right. You remember in the rate independent plasticity, phi star was either 0 or infinity, right. So, that is 0 phi star. So, but it appears only in phi, okay, and this is the rate dependent part, which is a function of mu. So, if mu is 0, you get only the rate independent plasticity. Okay. The final form therefore is this for phi, the dissipation potential, right. You see everything, the heat part, the viscoplastic so called regularization part, but we already know based on our discussion that this has a physical mooring, physical grounding, and this is the rate independent part, right. So, this is all about our today's talk. So, our next job therefore will be to use this phi that we have derived as part of our objective functional, you know, script j, which is basically psi dot plus phi, right, remember, or the discrete counterpart of that objective functional, in order to do a variational principle and hence solve this problem for all the unknowns using a discretized, time discretized finite element framework. That is what we will be doing for thermo-visco-plasticity in the next class. So, till then, goodbye, and I hope you are enjoying the course. Thank you very much for your attention.